So this is going to be a tutorial on effusion and diffusion type problems. We did these yesterday, and we're going to revisit them. So for all problems related to effusion and diffusion, you're going to be working with this as your basic equation. There are three major types of problems that we can do from this base equation. And those are the three types that will be on your FIP, and then the three types that will be on your test. So we're going to look at each of them, starting off with a problem where we are asked to simply compare the rate of effusion of two different gases. So here we're being asked to compare the rate of effusion of Cl2, that's chlorine gas, to methane, CH4. So this is a nice easy one because we don't really have to rearrange anything. You know the mass of chlorine gas and you know the mass of methane. Go ahead and figure those quickly. Okay, so we've got our masses for each of these, and we're going to plug these in. Okay, so we have our numbers put in, and somebody asked, does it matter which one goes on top and which one goes on bottom? It doesn't. But obviously, depending on which one you put where, you're going to get two different numbers. This is one of those kind of problems where you can get the correct number and still get the question wrong, because just like with limiting and excess, you have to know what to do with the number that you generate. So, now I will say, if you put the heavier gas on the top of the mass part of the equation, you get a number that's a little bit easier to understand and work with. Okay, so we're going to get a number, a single number out of this. Who's got a number so far? So we have our number, 2.1017719, etc. We're way beyond the sig figs we can have, but is equal to the rate of methane effusion over the rate of chlorine effusion. What does that mean? The thing to remember when looking at these is you're going to get a single number, but in fact it's a ratio, which means there is an invisible 1 underneath that. So what we're saying is that methane effuses. The thing to remember is that there's an invisible 1 under there. And what we're saying is that methane effuses at 2.10 times the rate of chlorine. Okay? Methane effuses at 2.1 times the rate of chlorine. Does that tell you that methane effuses faster or more slowly than chlorine? Faster. More than twice as fast. Is that consistent with what you would expect based on their masses? Yes. Methane's smaller, it's lighter, it goes faster. So, to make a quick visual of this, okay, so what this means is if we have a 3-meter long tube of some sort, and at one end of one of these tubes we put a chunk, a mass of methane gas, and at the other end of the other tube, we put a chunk, a mass of chlorine gas. In the time that the methane can travel 2.1 meters, the chlorine is only going to travel 1 meter. Okay? So the methane will travel farther in the same amount of time. It's moving faster. It's effusing or diffusing at 2.1 times the rate of the chlorine. The question was asked, what are the units on this thing? What are the units on this? Well, this was grams per mole. This was grams per mole. Grams per mole cancel. What are the units? What are the units in a ratio? All ratios share a common answer here. There are none. Ratios are unitless. They're just a comparison tool. So there are no units here. Okay, so if you think back to the sentences that we made with limiting and excess reagents, this is the same concept. What we're saying is when we have this problem set up where we have our ratio and we have the two gases that we were comparing, this gas, CH4, effuses at whatever number's on top here, 2.10 times the rate of whatever's on the bottom here. Okay? Does that help? Does that make it easier to understand? Okay. Now, what would have happened if we had randomly flipped those numbers and we would have gotten a different kind of number? So let's do that as an example. So the question was, how do you know that 2.1 goes with the methane? These numbers are connected. The top parts of these ratios are connected. The bottom parts are connected. And so if you remember, we go back to this meter stick idea. In the same amount of time that methane can move 2.1 meters, chlorine can only move 1 meter. So does that clarify and help with that? Okay. So the question always comes up, well, it's random which one you put on top and which one you put on bottom. What if I had put the lighter one up top and then I get this number, 0.4757, instead of the 2.1 that I had? Well, we can put a 1 under it again. So what we're saying here, so all we're saying now is that for every in the amount of time that a molecule of methane can effuse 1 entire meter, a molecule of chlorine isn't going to go a whole half a meter. It's going to go 0.4757 meters. So we still can put that invisible, that sort of magical 1 under there. So it's still a ratio. And now we would say chlorine effuses at 0.4757 the rate of methane. If this number that you get is less than 1, the first chemical you name is the one that's moving more slowly. Chlorine moves at 0.4, roughly half the rate of methane. Does that seem clear? Let's record that. A lot of people find it easier to deal with a number greater than 1 to basically deal with this number. So if you want a number greater than 1, you just need to make sure that your heavier element is always up at the top. That's it. You want your heavier element on top when you're doing the masses.
Oh, like, okay.
All right, so that's it on doing those kind of problems, just comparing the rates of effusion of two gases. Now we're going to look at the case where you're told that you're given two gases, or given an unknown gas and asked to find its approximate molar mass. Okay, so this is the second kind of problem you'll see, where we have a known gas and an unknown gas, and we're looking for an approximate molar mass. At this point, you are going to have to rearrange this equation. Now, here's the nice thing. This equation has everything that people hate algebraically. Nobody likes dealing with fractions. Nobody likes dealing with radicals. It's got both of them. So while it makes everybody really happy, because of the fact that you can assign which gas is gas A and which gas is gas B, guess what? You never have to solve for the one in the denominator. You can always set it up so you're solving for this. If you're solving for the one in the denominator, it's your own darn fault because you set it up that way. So in this case, we're going to assign gas X is A and our Cl2 is B. And I'm just making that note to myself. You don't have to do that. Okay, so we've listed the things we know, or we've started to. We're looking for the mass of our unknown gas. We have the mass of our chlorine gas, and we're told that the rate of effusion of gas X is 3.5 times the rate of the chlorine.
So we just put Cl2 or should we?
Okay, so I've got all my information here, and I've decided that I'm going to make that one on the top my unknown gas. So I've got my equation, and I need to solve for this. There are two ways to solve for this. You can either isolate this first, or you can get rid of the radicals first. I prefer to isolate my square root of mass of gas X first, so I'm going to multiply everything by the square root of the mass of chlorine. That gives me mass of mgx square root equals rate of Cl2 times molar square root of the molar mass of Cl2 over rate of my mystery gas. We start there. Now, remember, of course, we can do anything in algebra as long as we do it to both sides of the equation. If we square everything here, then we're going to get rid of our radicals. So far, so good. At this point, we're down to an equation where we have the mass of chlorine, and we have a relationship between the mass of our unknown gas and the mass of our chlorine. So let's go ahead and pop back to here, and we know that the rate of gas X is equal to 3.5 times the rate of chlorine. So we're going to substitute that. Okay, so here the rate of chlorine will cancel out, and this is rate of chlorine squared and 3.5 squared. So the rate of chlorine squared goes away. We're left with the mass of chlorine divided by 3.5 squared. Okay, so we were able to plug in numbers now. We've got 70.9 grams per mole divided by 12.25. And what's our mass of gas X? Okay, so we've got our mass of gas X, and we can have, I think, 3 sig figs here. So we're going to have 5.79 grams per mole. We're not going to get a real exact number for these. We're not getting a precise molar mass because the rates are not a real precise comparison. So it's going to be a little bit rough. So the 3.5 in there is not a measurement, it's a rate. And so it doesn't contribute to our sig figs. The only thing we've got for sig figs really is the molar mass of chlorine. So let's do the final kind of question. If you remember when we did this original derivation, we substituted the rate of effusion in for something else, the velocity of a particle. And then we said we don't typically measure the actual velocity of particles. We certainly can't do it in here. It can be done. And so the last kind of problem that you could see, and this is just like number 3 on page 355 in your book. Yeah, there's one in the homework like this, where you're given the mass of one particle and its velocity, and you're asked under the same conditions for some other chemical, what would be the velocity of that particle? So again, it's just algebra, it's just 3-part algebra. We'll probably run out of time here, but it's just like number 3 on page 355. If you look at your book, that is a sample problem or a practice problem, so the answer is there for you. Same thing, you're just solving for one of the variables. Okay, so we're told that under some given conditions, it doesn't matter what, at some temperature, at some pressure, a molecule of chlorine gas, Cl2, has a velocity of 32.9 meters per second. At the same temperature and pressure, what would be the velocity of a nitrogen molecule? So we are solving for one of our velocities. Again, you get to pick which one goes where. There is no reason to have to solve for what's in the denominator. You can always assign it to be the top. So let's draw this. Okay, so I've set this up the way I want it. So I'm solving for my nitrogen. It's not in the denominator, N2. Square root of the mass of chlorine over the square root of the mass of nitrogen equals velocity of nitrogen divided by velocity of chlorine. So to solve for that, we just multiply both sides by our velocity of Cl2. So in algebra, as long as we do the same thing to both sides, we can do anything we darn well please. We're going to multiply both sides by the velocity of chlorine, and we have, at this point, it's just a matter of plugging numbers in to get the velocity of your nitrogen. Does anybody need to see any more than that? Do we want to finish it out, or you can finish that on your own from there? So number 3 on 355 is the same kind of problem. In this case, you do not have to get rid of those radicals because you have numbers to plug in for both of them. As long as you have a number to plug in under that radical, you don't have to get rid of it. You only have to get rid of it if you're solving for it as a variable. Okay,
Yeah, I like
that's it, folks.